Alright folks, welcome back. This is our last video before we start actually conducting hypothesis tests in our new analysis of variance framework. So, last video we talked a little bit about the different types of variance that we calculate, the idea of between groups and within groups variance, and how we use within groups variance as a sort of basis of comparison. Next we are going to break that down a little bit farther and talk about how it plays a role in our main test statistic in ANOVA, what's called the F ratio. Then we'll talk a little bit about the assumptions of the ANOVA and leave things off, start up fresh with an actual walkthrough of a hypothesis test. So, to recap, when we calculate between and within groups variance, what we are looking at is we're trying to isolate different things that can cause scores to vary. So when we look at between groups variance, again, that's how much the different groups or conditions differ from each other, like how far apart their means are from one another. When we look at that, we can say we can break this variance down to a few different possible causes. Between groups variance could be caused by our independent variable or our quasi-independent variable. This generally gets called a treatment effect because it is oftentimes some kind of a treatment you gave people. So if that IV or quasi-IV is at all related to any differences between scores, it's going to be related to the differences between groups. It's going to cause those conditions to differ from one another. The problem is that that's not the only thing that can make those groups differ from each other. It could also be individual differences. If I'm measuring, say, alertness, some people are naturally more or less alert than others, regardless of anything we do to them in the study. If I'm measuring people's self-esteem, same things. People are walking into the study with different pre-existing levels of self-esteem. So those individual differences, we try to use random assignment to cancel them out to make sure that, again, people who are relatively high, low, and in between are evenly distributed among our conditions. But random assignment is not perfect, especially with smaller sample sizes. It could just be due to a fluke of random assignment that just most of our alert people wound up in one group and most of our sleepy people wound up in another. That can happen. The odds of that go down as you measure more people, but it is always possible. So the differences between groups could be driven by those individual differences. Just on average, people in one group were already different on the DV than others. Then we have kind of a catch-all term called error. Just inaccuracies in the way that our sample represents our population. Maybe you get a sample that just happens to be way above average or way below average or slightly above or below average. That would be a source of error. So those are the three things that could cause our conditions to differ from each other. Notice two of them we don't care about. So we know that those three things are combined the possible sources of our group differences, our group variability, but we don't know which is which. We don't know which one's the most influential or to what degree they influence people. So we're going to try to isolate that with a basis of comparison. Remember, just like in our t-test formula or z-test formula, we took the difference between two means, but we standardized it. We gave it context by dividing by the standard error. Same sort of idea here. When we compare people within the same groups, we're kind of coming up with that basis of comparison. So we're saying what's sort of the natural fluctuation in people's scores when the IV isn't differing from one person to the next, when people are in the same group, say drinking the same caffeinated drink or whatever we're doing to them. Here, what can cause those scores to vary? Well, individual differences could. Some people are already more or less alert, and that's guaranteed that people will vary to some extent on that DV. And so that's going to drive to some extent the differences between people in the same condition. And then we again have that error factor where, again, it's possible just that the people that we drew just are from the periphery of the distribution. They're really far away from average, something like that. So we calculate those two variances, and again, notice the IV, the treatment effect, can't be influencing within groups variance because the people are experiencing the same level of the IV. It can't be causing their scores to differ from each other because everybody's in the same condition, everyone's experiencing the same level of the IV. So we take these two variances and we calculate what's called an F ratio. The F ratio is a ratio between variances. So specifically, we take the between groups variance, that becomes our numerator, within groups variance is our denominator. Here's the logic. Between groups variance we know is made up of treatment effects, individual difference effects, and that error. We don't know which is which or how influential each one is, but we use as a basis of comparison within groups variance, which we know is made up of just individual differences in error. What's the logic there? Well, you should be able to think about this from just some basic division stuff. The logic there is that the individual differences will cancel out, the error will cancel out since both are present in both numerator and denominator, and we're going to be left with a number that's going to be a pretty good estimate of how influential that treatment effect is. So the bigger the ratio is, the stronger an indication we have that our treatment is doing something, that it is responsible for some of the variability between our groups. So this is kind of a neat little way of trying to isolate that treatment effect, if there is any. The more influential the treatment is, the more top-heavy you'd expect this formula to get, because it's only going to affect the numerator. The denominator will be unaffected, and you'll get a bigger F ratio. The less influential the treatment effect is, the more even you would expect numerator and denominator to become, because again, treatment's not doing much at all. Well, now you have individual differences in error divided by individual differences in error. You'd expect that to be pretty close to 1. So that gets combined into this F ratio. It is a new statistic. Remember, both t-scores and z-scores boiled down to just how many standard errors apart are these two means that we're comparing, or in the difference score, how far away, how many standard errors from 0 are those difference scores. The F ratio, again, is a little bit different than that, because again, it's just how much more between than within groups variance is there. So what this translates to is that our comparison distribution now changes. The way in which we represent it changes. We use instead a distribution of F scores, which is, there's a table for this for the critical values there, but the F distribution, like the T distribution, changes shape based on the number of groups that you have and the number of people that you have as well. So those degrees of freedom now again define the shape of that F distribution. Here's the trick, because we now have a couple different dimensions, just how many people we have, but also how many groups we have can vary. We now have 2 different degrees of freedom that we calculate. So degrees of freedom between groups is sometimes called our numerator degrees of freedom, and degrees of freedom within groups, which is sometimes called our denominator. Again, when the treatment is really influential, we expect that F ratio to be big. When the treatment is not doing anything at all to scores, we expect that ratio to be small. So this is our first point of emphasis for our Module 10. And again, the entire point of that F ratio is to try to figure out, to try to isolate what effect the treatment is having. The single best way of doing that is having that basis of comparison. How much do people in the same groups vary from each other? Then how much do people in different groups tend to vary from each other? Any effect that treatment is having is only coming up in the between groups. And if you expect individual differences in error to be roughly equal between and within groups, then you would expect, again, to get a pretty good estimate of what that treatment effect is doing. A perfect estimate? No, probably not. But overall, especially as you get more data and as your study design improves, this ratio is going to be better and better at trying to isolate and estimate the effect of the treatment. So here's what our distribution of F ratios looks like, our comparison distribution. You should already be able to pick out a few things that are different from this than our T distributions and our Z distributions. First, this is not symmetrical anymore. Normal curve and T distribution were both symmetrical. This has a different shape. What shape does it have? It is positively skewed. Notice we have a tail going off here to the right. Also notice that unlike the T and Z distributions, we have a hard floor. F ratios can never be below 0. The reason why? Variances can never be below 0. Again, just if you don't remember from Module 4, when you are calculating your variances here, if you get a negative number, you goofed. Stop. It is guaranteed to be a wrong answer. Variance cannot be negative. The only way variance can be 0 is if every single score is the same. So you can't have a negative variance, so you can't have a negative F ratio. Also notice that our critical region, our region of rejection, is only in the right tail here. This looks like a right-tailed test, even though if you remember we said these are all two-tailed tests. Here's the reason why. We're not dealing with deviation scores anymore, translated into z-scores or t-scores. We're looking at the ratio of these variances. The more influential the treatment is, the bigger and bigger you would expect that F ratio to get. And at a certain point, you get F ratios big enough that you say, gosh, it's really unlikely I'd get a ratio like that if the null hypothesis was false, if these populations really were all the same. By the way, see if you can guess for a minute what the mode of this distribution might look like. What's the most common ratio going to be if the null hypothesis is right? Well, if the null hypothesis is right, the treatment effect is 0. So you have individual differences in error divided by individual differences in error. You're going to expect that to be right around 1. So 1 is the mode here. The farther above 1 you get, the more improbable those scores become, those ratios become if the null is true. And when you get past a certain point, defined by alpha and degrees of freedom, you'll be in that region of rejection. You're going to be able to reject the null. And again, we define the shape of this by saying it's an F distribution, also calculating those 2 different degrees of freedom. We'll wrap things up with a little bit of house cleaning, some of the assumptions that we make in an ANOVA. First, we assume normality, which just means whatever dV we're measuring, we assume that it follows a normal curve in each population that you take your samples from. If you remember from the sampling distribution stuff, that's something you can be pretty confident about, that the variable follows a normal curve in the population because of the way the sampling distribution works. But that is one of the assumptions that we make. We also assume what's called homogeneity of variance, which means the variance in those dV scores is also essentially more or less equal for every population you're comparing. And we assume that random assignment has been used, and that has led to extraneous variables like those individual differences, like just that pure sampling error, that those extraneous variables are equally distributed. Now you might be looking at this and thinking, this might not always be true. Maybe normality always happens, but it's pretty unlikely they'll all have exactly the same variance. Fortunately, the ANOVA is what's called a robust test, which means, again, even if these assumptions aren't 100% true, even if the true state of affairs is a little bit different, we tend to still get very accurate results. But the closer we get to all of these being completely accurate, the more accurate the ANOVA becomes. But it still holds up pretty well, even if those 3 things aren't 100% true in your situation. So that's the end of our setup. Our next video, we're going to actually walk through a hypothesis test in ANOVA to see how this whole process works. Really important one there. See you there.